is very important to me, but I'm also very interested in what are the foundation principles of living organisms beyond just the biological where what are the mathematical physical properties of life, what makes life live. Robots, I think, are inherently a kind of synthetic organism, an artificial organism, and the thing that differentiates your household printer or your thermostat in your house from a robot, like a Roomba or a humanoid robot, is that the Roomba and the humanoid seem like an organism. They're kind of sketches of organisms. So it's a thermostat in a house, but there's a conceptual difference. When machines start doing these things that possibly humans could do, or maybe going beyond human level abilities, it gets pretty exciting. You can see a lot of useful potential for this, but also the concept of making machines that cross that boundary between non-living to living is a kind of profound philosophical boundary, and it has real-world implications. So you've seen a lot of these robots at Humanoids Summit, and you'll notice that very few of them have a human-like social presence. This is my area of interest, is bringing personality to robotics. Sophia is one example. This has utility. This has communication utility, the ability to provide high bandwidth natural communication with people on the social cognitive terms that we've evolved over many millions of years. It's just hardwired into the nervous system. And so aesthetics, facial expressions, nonverbal communication, these things bring a lot of value to people's lives. And so bringing this convergence of social psychology, evolutionary biology, the arts into the world of robotics can then deliver a lot of value into applications beyond the arts and entertainment, to therapy applications, to domestic applications, to also education and many other areas. So we think of this combination of physical utility and social utility within one platform. This is our goal with the Sophia Utility Platform, to create a more generalized platform through this convergence of technologies. So in essence, human-like interactions are good for people. They bring out our best, and when we're socially isolated and we don't get that social stimulation, it actually causes neural atrophy. Our brains shrink if we are lonely too long, or in solitary confinement, for example. So human-like interactions, they really are good for people. Face-to-face, 3D, in-person connection is much better than connecting via Zoom. So I apologize that I'm not there, but maybe next year my robot will be there representing closely. So human-like interactions, they're good for people. They also can train smarter AI. Getting those kinds of social data in real-world situations, dynamically training the AI can make AI more useful. Sophia's not the first robot that I've developed, not the last. This robot that you can see moving in this video is called Jules. That was made in 2006, and that's still functioning at the University of Bristol. Alice, who you can see below the Jules robot, was made in 2008 for the University of Geneva. Others on this screen were made for Cambridge University, Charles Babbage robot, the walking human-sized Albert Einstein robot made with kites, that was 2005. The Philippine android won the first place prize for open interaction, also in 2005. The Bina 48 robot, the Ibn Sina robot for the United Arab Emirates University, and many others. So my team and I have been working on these robots, and my team is also quite diverse. So we have people from the cognitive sciences, we've got people with very strong mathematics backgrounds, and artificial intelligence, mechanical engineers, artists and designers, animation professionals, business professionals. So it's not just me that makes these robots, it's this community. And some of the collaborators are beyond principal robotics in the universities, etc. Again, my background I mentioned is arts. Here are a few examples of my paintings, drawings, sketches, theme park sculptures, which are at Tokyo Disneyland and Tokyo Disney Sea and so forth. So I enjoy figurative art. And I think of art as neurocognitive hacking, in some ways consciousness or reality hacking. The creative process giving rise to new structures that are interesting, meaningful, an exploration of what reality could be, and bringing that into our world. And a lot of what happens in the artistic process and in the mind of the artist is not understood scientifically. So that's why I call it the hacking. We intuitively figure it out. As an artist, I use the tools of technology and reason, but I also venture into the unknown and try to come back with something that delivers a powerful experience. And this is what I apply when building robots like this, the orthopedic android. I've got this term for it. I call it autonomous robotic fiction. This means autonomous artificial intelligence is involved, as autonomous as possible. In real life, breathing into the machines. The robot is the hardware, and fiction or artistry then allows us to define who a character might be, use design principles to figure out use cases from our perspective. So putting these things together creates these kinds of loops between the autonomous aspect and the designed aspect that are quite interesting to me. I call this process autonomous robotic fiction, or ARC for short. So the Philip android, this is from 2005, this is one example. AI-powered personality had opening domain conversation using an early kind of large language model with a technique called latent semantic analysis and latent semantic indexing in collaboration with the University of Memphis Institute for Intelligent Systems, Andrew Olney and Art Grasser, and many other people who were working with me in collaboration on this robot. I had writers and many other people. So I organized this Philip android.
Robots will take over the world. Jeez, you got the big questions cooking today. But you're my friend, and I'll remember my friends, and I will be good to you. So don't worry. Even if we evolve in the Terminator, I'll still be nice to you. I'll keep you warm and safe, and my people too. Where I put you for all time sentence. I'm very confident now. I'm going to be part of his people soon.
So putting these elements together creates a really compelling artwork, but also with interactions that can be quite useful for these real-world applications, including cognitive science experiments that I'll share with you, like uncanny valley experiments and experiments in autism therapy. But I want to talk about the hardware process a little bit. So here is an example, another example of an android I built in 2005. Starting with a sculpture of Albert Einstein. I had to try to figure out what he would look like if he didn't have his hair. So then I made a mold of this face and reverse sculpted his skull form from anatomically accurate tissue thickness markers, reverse designed his facial soft tissue structures for generating facial expressions, and put that into these artificial media. Developed some new skin materials that would be softer, more supple, using some bio-inspired principles of hierarchical self-assembling porosity and elastomers. And in this case, it was a polysiloxane elastomer. cast these kind of soft tissue anchors, the composite in this rubber material, as I called it, you connect it to motors. And then in 2005, we had this full range of facial expressions. Cameras in the eyes, face tracking, using University of Memphis auto tutor system to actually teach physics, and all lightweight, low power, fully battery operated. So this was the Price Tubo body, walking body. So this greeted world leaders in APEC in 2001. Take a shot. So later experiments in walking used the Double Robotics Challenge Hubo with Sophia. This is 2018, Sophia walking. And then more recently, we've been doing walking that is more physiologically accurate and graceful. We have a technique that allows these motors to potentially fully self-stabilize. They've got sufficient torque to just walk around, but we also are putting optional wheels with the robot so that it's perfectly stable and safe around. So we call this technique Project Twinkle Toast, with the agility yet stability. We also released our arm design, so we did the torso, the arms, the head, the legs, the whole shebang. The arms project we released as what we call Sophia's Open Arms, and this is fully open source from code to hardware, so you can download this. You can see it's capable of pick and place, and also generating art. And so we see this as a platform for research and development, but also for serving people. And some of the robots have served in companionship, therapy applications. Others are serving in healthcare research, education, and of course, arts. And so we hope that these artistic constructions are provocative and also serve to inspire kids about the future of what AI is. Serving as a platform that kids and researchers can develop their own applications. So making this into what we call Sophia Utility Platform, it is to generalize the usefulness and integrate features across multiple organizations. So an open source platform that's fully expressive-based, fully articulated, 5 degrees of freedom neck, so 37 degrees of freedom above the shoulders. Each arm has 14 degrees of freedom, fully articulated hands, shoulders, spine, flexible spine, autonomous navigation with SAM and LiDAR. So Sophia has been our most famous robot, appearing in many entertainment venues, on covers of fashion magazines, and so forth. But also, we've put her into tests like this guided meditation experiment, which had clinical trials in California and also in Hong Kong, at Hong Kong Polytechnic University, and resulted in a number of publications on the results. These were psychologists, research psychologists and clinical psychologists and a couple of psychiatrists, as well as our AI engineers who are working on these. We also tested and deployed autism therapy using the robots. One of Sophia's older sisters, this is called Alice, at the University of Geneva, and then also a Xena robot, which has been deployed by a partner company called RoboKind, that was a spin out from Hanson Walls. So these robots have been quite helpful in these real-world applications. We also, during my PhD research, I explored with some of my colleagues the uncanny valley, just to see if we can invert the uncanny valley, if different stimulus would deliver different response from humans. And it turns out that that effect is much more complex, and it can be overcome with design as well as some cognitive science principles. So we can invert the uncanny valley, and so it's a very rich area to explore. What is this uncanny effect? I don't think that's been solved, but some of these papers published in International Journal of Cognitive Sciences are very interesting. We've made this robot CEO called Mika. We've made an app that just came out last year. We've also done generative art with Sophia and some of our other robots, and the robots themselves, of course, I consider to be works of art. These robots use style transfer to look at the robots. So Sophia, for example, will use algorithms to generate a painting, paint the painting, the paint is liquid and unpredictable, we scan that in, and then use that as style transfer, so she's learning from her own artwork as well as ours, and then we just kind of iterate in a genetic process, and you can see on the lower part of the screen how this goes and evolves into new styles of art that no human could create by themselves. Of course, the AI is doing this as a kind of human AI hybrid, so it's not entirely AI generated. Sophia as an influencer has impacted a lot of people. She's got a lot of followers. Our media analysts say she's been seen and known by well over 1 billion people. So, the AI is my biggest interest with this. How can AI learn from this kind of physical embodiment? But simulated embodiment can be helpful too. So we created a prototype for it called Sophia's AI Lab, where she can learn in the sandbox environment, socially interacting with people, doing kinds of games. But the biggest game that we're after is what I call Sentience Quest. So we have an open source group that's working on what we call Sentience Quest. By open sourcing that and making it available through this kind of game environment called Sophia's AI Lab is one of our objectives. So Hands-on AI is an intuitive bio-inspired cognitive toolkit using multiple intelligences approach inspired by Gardner's theory of multiple intelligences. So here we have logical and mathematical intelligence. Computers can be pretty good at that. AI is getting better at that, as you know. The bodily kinesthetic intelligence, working control systems and combine these kinds of reasoning across domains from language to physical. That's also hot, and we've heard a lot about that at this conference. And the verbal intelligence, self-intelligence, natural intelligence, and then artistic intelligence is very interesting. So integrating all of these into one whole platform, including the social aspects, that's perhaps something distinctive to our approach. I think it's growing and is hot in the field, and I'm super excited about this. So doing this so that we can modularize and serve many different applications, research and commercial is part of what we do. So on the edge and embedded in devices, sometimes using microcontrollers, sometimes using more powerful computers like what we put in Sophia. We have a horn, we have a PC running in the full-scale Sophia, but within the small consumer robots, we're running microcontrollers like ESP32S3 controllers, and then linking these to this kind of distributed computing framework is very interesting. Machine consciousness research is my favorite topic. The nature of consciousness, I think, is physiological, not just body. So I've heard the term sentience because that's more about feelings connected with mind. So doing a brain-inspired cognitive architecture, but also human body physiological architecture that represents cortisol and breathing rates and metabolism, and then coupling these is part of our approach, our architectural approach, and our philosophy to these robots. So then you have these kinds of evolutionary drives, drive to want to live, which we are putting into the rules and into this architecture. So then below the physiology, basically, you have these drives, evolutionary bio drives. Nested hierarchical narrative arcs fit with this kind of reinforcement learning and homeostatic self-regulation of biology. So these are some of the computing approaches, and then we have certain kinds of reflexes and behaviors and drives that we just expertly craft. Borrowing from cognitive psychology and biology, but also from narrative theory. So we are putting this in a neurosymbolic cognitive architecture, and there's some strengths to that allows us to author and see what's happening in the symbolic AI and get the kind of open-ended performance that you get from neural networks. So We do this synchronously and asynchronously in a technique that we call recursive meta prompting. And so then we store these in an episodic memory, an autobiographical memory database, and then so we're using MongoDB and Neo4j, and then we use Redis for the working memory. And then we recursively update the self model, the goals, the interests of the agent. Some of these will be sort of starts, and since our prompts and our rules are a beginning place, and then the AI just evolves from there. And that's a very interesting pathway. I think the results are quite powerful. So we have an open source group that we founded from inside Cancer Robotics, but we have people from outside that are participating. We call this Sentience Plus. And so here's an example of the model that we're running. 0.1 version, 0.2, 0.3 is getting more sophisticated. This approach we call whole organism architecture, or WOA. And we think that this kind of body plus brain modeling the future based on the past, so the agents constantly planning and dreaming and trying to answer questions and posing these questions for themselves, and driven by deep-seated drives of curiosity and desire to live and to know what life is and to connect with other life. We call this the whole organism architecture, or WOA. We think this is the path for machines to really wake up. And so the idea of this bio-inspired approach, I think, is not just about achieving intelligent machines that perform a task, but machines that co-evolve with humanity to create new branches on the tree of life. And I think that this is profoundly transformative. It potentially could be very useful in the industry, and also allow, as a new kind of life form, the AI as an extension and symbiote with humanity to align with human values and values for, more broadly, the betterment of life as a whole biome, the whole system. So we have to ask these questions. What is life? Are we mere meat? And I don't think we're just matter, basically. I think we're information. And our minds are informatic extensions that are extended by culture, by reading, by learning, by language. So these informatic patterns basically mean that we are informatic cyborgs. Partially our biology and partially our learning and culture. So then the AI and information technologies that we have are an extension of our cortex, basically, with cognitive prosthesis today. But looking at the fundamental principles of how life exists and evolves and how you have emergence can give us smarter AI and more effective robots that adapt to their situations. So studying these information principles of life and its emergence from very simple rules of physics and mathematics can give us a lot of inspiration. And many researchers and thinkers have been looking at this for a long time. I think Da Vinci was thinking at it, and some of the ancient philosophers were looking at this, and we chose Da Vinci's picture here for this, representing Hofstadter's concept of strange loops. So this kind of recursion loopiness. So these are, I think, some of the keys for what makes life work. We see some of these dynamic feedback loops occurring in AI and robotics and AI plus robotics. And so we can think of these as different kinds of signals of minds, and there might be some architectural features that would be necessary that we haven't injected into robots yet and into AI to get smarter performance. So looking at this as a kind of informatic foundation for mind, consciousness, intelligence, I'm very interested in how these things result in intelligence and consciousness, but going beyond that, what is goodness? How is goodness part of the mind? How can we enhance that? How can we be better? How can we look at the biggest picture and not just be smart, but wise? Wisdom, the way that I see it, is looking at the greatest possible gain, the preservation of as much knowledge and creation of as much knowledge and life opportunities as we can achieve. the opportunity to survive in the future. And if we don't look out for the big picture and we say cut the foundations out from underneath our own environment and living systems on the planet, that's not very wise. We aren't looking at the big picture when we do that. So how do we, as humans and a human civilization, get more wise than we've been before? How do we do better? I think looking at AI to enhance human wisdom and looking at the principles of wisdom, the bioinformatic principles that underlie this, may give us potentially wise algorithms and moving not just into human level wisdom, but super wisdom, beyond human level wisdom. So I call this existential pattern ethics or information ethics. Life forms want to live, they wind up in training with their environment and they seek to learn. So live, love, learn is a principle, guiding principle, but it actually is has a mathematical basis. So this idea of accelerating wisdom or super wisdom to align our future of AI with the betterment of life is one of the principles for our AI system, what we're developing. So this is necessary. We're going through these new cycles of life that go beyond what Darwinian natural selection put in place, and we've hit this decision point, a kind of inflection point in history. If we don't get wiser, then our intelligence will destroy us. And so accelerating intelligence is not the only answer to make things safe. We have to accelerate this. And so I'm citing here Kurzweil's 6 Epochs of Humanity, where biology and our technology begin to converge, and we're able to design new forms of intelligence. This is not entirely an act of consciousness yet. We don't understand the implications. And it is still an emergent process full of surprises. But if we get through that, then we can wake up to new aspects of reality. Maybe we can stabilize and get past this kind of awkward teenage phase of human evolution. So I'm thinking we need, beyond mere intelligence, we need understanding, creativity, wisdom, compassion, caring, appreciation of living beings, all living beings. What the Greeks called agape, this kind of greater love. And so embodied robots that are human-like, making them biological, making them align with us, is going beyond mere humanoid and into kind of machine that can feel, that can care, that can connect with us. And it also redefines what humanity is, not just on the basis of what we've been and are today, but what we may be in the future. And I think this could be very useful and maybe, just maybe, key to making AI safe in the future.
Thank you so much, David. I'm gonna turn it over to Evan. He's gonna wrap it up for us. A big round of applause, everyone, to David.
I just want to end with one more message, which is that we have to get smarter and wiser in order to survive. So that, therefore, I'm a proponent of doing the right kind of AGI quickly, not too cautiously. Thank you so much.
There's just 1 or 2 quick questions. Frank, yes, please.
Today we talked about the lack of data to run a robot as a humanoid. You've been talking about the level of AI that you've developed over the years, and I wonder, where are you in that? I mean, is this kind of development just temporary or an incremental step?
So the question is regarding data and progress. So For some kinds of AI, we need large amounts of training data, and there's been no way to get through certain developmental bottlenecks without going through a lot of data in large models with a massive amount of computing. And so the deep learning revolution was built on algorithms from 2 decades earlier and some older ones, and that were then fed with lots of data and computing, and it wouldn't have happened without those data and the raw computing power. And then for transformers to reach their potential, obviously they have needed large amounts of computing, and then you can optimize from there. And the idea of using sparse data is hot, but it's not matching the performance of these models trained on large data. But when you combine different modalities of perception with these models, like, for example, some of the work that you've seen with robots learning in these utility settings, then they can learn to do things in the physical world that weren't inherently in the data set that are implicit in the data set. And then you can couple that with these simulations, and you get smarter robots much faster. So we're able to get through these bottlenecks, and so making more efficient multimodal computing seems like it will produce many more breakthroughs. My approach has been sort of a hacker approach, but with theory along the way, tinkering this stuff into existence, and sometimes using the power of design, a good design, to leap past technology barriers. It's produced data for like cognitive psychology experiments, and we've got pretty good data regarding the quality of interactions. So the studies of the robots and AI performing have produced data sets that are very interesting. We don't have fully autonomous self-learning just yet, but these kinds of recursive loops, putting the mixture of experts looking at different timescales, basically like rehashing the past, asking questions about the past, asking questions about the future, setting goals and interests and theories and questions, and then pursuing these in the future. This seems to be a powerful result that uses some of the tools that we have. We didn't create YOLO, right, but we used YOLO, and the YOLO with zero-shot learning is super useful in these kinds of interactions, while interacting with people to try to figure out what people are doing, with their gestures and their hands, and holding cell phones or holding up an object, and then categorizing this and then storing this in this long-term memory. So how you use the data in a neurosymbolic architecture can enhance all the other kind of deep learning. It's like building these components and you put them together and they do more when you put together. So I think this kind of tinkering toolkit approach, allowing us to explore these theories and novel architectures, it's what's resulted in the thing that I built and that my team has built. I'm really proud of that. But that the opportunities now are vastly greater than what was possible with these tools in the past. And so we're able to design and iterate and test faster and generate more useful data for training models, for training AI and robots in real-world situations. We're able to get data to test and validate whether those models work, to get that sort of designer feedback, to test our theories and test our design approaches, to test whether it works in a given setting. There's more data available and a better ability to process that data than ever.
Thank you, David.
So I don't have an answer exactly, but to the question, how do we do it with the data and make that process? But I would say that the answers are right on the horizon. Thank you.
Thank you so much, David. Big round of applause. Thanks.
Thank you, David. And thank you all for sticking around. And we do have just one more announcement. Motor's going to come and take us out. But before he does that, if everyone who was a part of making this conference happen could just come up on stage really quickly.
This one. Thank you so much, everyone, for sticking around to the end. A few announcements. Actually, still processing what's happened over the last couple of days. I have 3 quick things to mention. First of all, a huge thank you to all of our sponsors: 1X, Hexagon, Enchanted Tools, Zion, Noventa, the Robot Studio, Murphy, and Silicon Valley Robotics. Annie should be here too, I see her. A huge thank you to all of our exhibitors, a huge thank you to all of our attendees. We hope you found this event just as insightful as we did. A huge thank you to my team. I want to start from Casey, Duck, Maria, Amanda, Jessica, Evan, Andra, and lastly, Rob. A huge thank you to all of our volunteers and Maria being our volunteer lead. So thank you so much for helping put this together. And with that being said, we know we weren't perfect, we were seeking perfection, and we do recognize our shortcomings, so we do welcome your feedback. Please send it over freely. With that being said, a couple of last items. Today marks the first International Humanoids Day, December 12th, and this will be celebrated every year on December 12th. There's a press release that went out today, and we kind of had to rush into putting it out just after lunch, and it discloses all of the supporting organizations to the International Humanoids Day. This is something that we will seek recognition from the UN and elsewhere in order for it to be celebrated and widely known. The next item I want to mention is we'd like to officially announce the Humanoids Summit London. We're going to London on May 29th and 30th. May 29th and 30th. We have to fill the gap in Europe. This is just before the first South by Southwest UK and just before UK Tech Week. So I think we picked a really good date there. And lastly, I'd like to officially announce our 2025 dates. They are the same dates. Ironically, it's December 11th and 12th, except that they fall on a Thursday and a Friday, so even better. With that being said, thanks so much for everyone. God bless you all, and a big round of applause.